Hello everyone, thank you very much for the invitation to present for the PyTorch Day. So today I'm going to talk a bit about the open sourcing we've been doing at Kyutai. So first word about us, so we are a non-profit lab based in Paris. We opened about a year and a half ago. And so our goal is to do open science and open research, open source research. We have an initial focus that has been quite around multimodal large language model, but in general we're interested in anything that would be useful for core machine learning with a large potential for downstream applications. So we were just 6 people, and now we're about more than 20 people. We have a few more coming, so I'm not going to present the whole team, but basically we have both permanent researcher, engineers, and postdoctorate and resident PhD students, which is something that's very important in our mission as well, to kind of train the next generation of scientists. And we think that this is most efficient if like the next generation has access to
hand up a little bit.
has access like to kind of industry-like training capabilities as early as possible. And of course, I would like to thank our donors, so Xavier Niel, Rodolphe Sade, and Eric Schmidt, who permits us to do this work for the community. So first, why do we value open source? So I think there's 3 motivations. The first one is for scientists. And one of the pillars of science is reproducibility. And you want to be able to do like fair comparisons to existing methods, and that can be hard if all you can do is to trust numbers that have been obtained in conditions that you don't necessarily know entirely. So by having open source model, it's possible to really understand how previous work achieved a given performance, to test it for new applications, and that allows to measure meaningful progress. The model we open source can also serve as a foundation for new research project, either directly as pre-trained model or for fine-tuning, or even just inspiration. And of course, the ideal case is to do like full dataset and training code open sourcing, which I've done a few times so far in my career, but it's very hard to hit this kind of ideal goal with every single project, and it's of course a bit time consuming. Then the second reason is basically for every AI practitioners, and I think personally I learned to program by myself in my room, just connecting to the internet, installing Linux on my laptop, installing GCC, going on forum, and what's really great with AI is that this really works like that as well. Like anyone who knows a little bit about computers can really get bootstrapped, and it's probably even easier today. So yes, we want to like be part of the open source community, help it grow, and allow people to build cool stuff. And finally, obviously, for startups and companies, so us, we are a non-profit, but we understand that training foundation model is extremely expensive. And basically, top funded startups can afford to train foundation models, but they're not going to cover all the possible applications. And so the more open source we have, the more likely it is that we're going to have some cool downstream applications, for instance, in accessibility, education, mental, physical health, and many more. So let's discuss a bit about the artifacts that we've released so far. So the first one that we worked on for the first 6 months was Mimi and Moshi. So Mimi, it's a general use, neural audio codec. I forgot the audio, it's important, obvious for me. But basically it encodes any kind of speech from any speaker in English or French into a stream of tokens that can be then used to train an audio language model, which allows many applications like text-to-speech, conversational models, translation models. So we just put it to the test with Moshi, which was a full duplex, which is a full duplex 7 billion parameter model. So full duplex means the model can speak at any time and I can speak at any time, and there's no explicit change of turns, which avoid a lot of issues of like you're talking to some voice mod, but there's some noise around because you're closing the fridge door, and then it's gonna think it's an interruption, and it goes back into trying to transcribe what you're saying, and so that allows for very fluent conversations. One of the downsides, though, is that at the moment those models are not as smart as like purely text-based models, but that's something we'll look to improve in the future. So I can give a video from when we learned. We're in Aquaspace, and now we have 5 months. I want to learn to know you a bit better. Why did you decide to join Starfleet?
I wanted to make a difference in the world.
Okay. How long have you been in Starfleet?
I've been in Starfleet for about 6 years.
Okay, that's a long time. I guess you've done a lot of other missions. Which one was the most exciting?
The most exciting mission was when we discovered a new planet with intelligent life.
Oh my god. So you can notice here some of the advantage of this full duplex approach is really the speed of the interaction. You have literally no downtimes. So the video you've just seen, we were hosting the model on an L4 GPU in the cloud. We also have a version that can run on a MacBook Pro, like latest generation, quantized, and all those models are open source. Okay, and one cool thing is that once we open sourced the model, actually there was a team in the University of Nagoya in Japan that made a Japanese version. And what was really impressive is that they did that even before we released any fine-tuning code base, and the whole pipeline is a bit of a mess, so it's pretty cool that they managed to figure it out. But now there is a fine-tuning code base, so it's a little bit easier.
早速なんですけど、今日はどういったご研究をされているかというか。
Japanese, but I have limited ability to know if it says something interesting, but from the popularity that in Japan, I guess it worked fairly well. Then a second model we released earlier this year is Moshi Vision. So here the point was to add vision as an extra sense to our model, while keeping some of the core characteristics of Moshi. In particular, the fact that the model is real-time and it's extremely low latency, and you can still have general conversations with it, so it's not just gonna do like image descriptions. And another objective was to try to do that in a kind of a lightweight manner, so we add only 200 million extra parameters. We train with a large amount of text image pairs, but we needed only, well, still a lot, but could have been worse. Like I guess there's only maybe 10% of the data that we synthesized to actual audio. So about 20,000 hours of synthesized conversation. So same thing, this one we have a demo online, and we have also open source model that can run on a diverse set of inference setup. Let's see a demo.
Hello, how can I help you?
Hey Moshi, so I'm at the beach right now, and I found this sign, and I'm not really sure what I should do. Can you help me out?
Sure. What does the sign say and where did you find it?
Well, at the beach, and I sent you a picture of the sign just now.
Okay, I'll take a look.
What do you see?
I see a yellow sign with a black triangle on it. It has an illustration of a wave crashing onto a beach. The text reads, Zona de Tsunami del Atacama in Spanish and Tsunami Zone in English.
Okay. And where do you think this one can be found?
This sign is likely located at the beach.
Okay. Then we switched a bit away from Moshi. We also released a 2B large language model supporting the 24 languages from the European Union, and watching the previous talk, I felt a little bit bad because I don't think we abided by all the top requirements for good evaluations. We did some evaluations actually with the translated data, which wasn't necessarily the worst, but not the best. So we will improve on that. Another cool thing that Edouard worked on that really discovered is, so there's been this concept of model soup, which was actually developed in part by Alexandre Ramé, who's now at Google. So the idea is you're going to take the average of different fine-tune of your models. So it needs to be a common pre-training, and then you're going to fine-tune it on different subset of data, and then you're going to average the weights. And somehow this is going to give you at least a good combination of the different capabilities that you add on domain-specific subset of your training data, and sometimes it can really give you at the end a better model than if you would have trained just on all the data together, fine-tune on all the data together. And in order to have some controllability, what Edouard developed is a Dactory, so it's a full pipeline for like HTML to text, starting from, for instance, from command crawl, doing like quality filtering, deduplication, and at the end, the capability to, like, let's say you have a high quality corpus, for instance, Wikipedia or technical books, and you want to identify in your huge kind of pre-training data stash data that's very similar to that. Well, thanks to some fast text-based text classifiers, you can identify the data that is the closest, assemble it into a subset, and then you can fine-tune on that. And here, so for instance, we can see that we can get a huge, so books here shows the scientific literature, so by extracting things that looks like scientific literature from the pre-training set, training only on that, you can get pretty good bumps in NMLU. But depending on basically what you want to use your model for, it might be worse to do the fine-tuning on one of those subsets, or do a model soup and average weights to share the benefits. And then a final one, EBKey, so it's a live translation model, simultaneous translation with speaker voice cloning. So it's speech-to-speech. At the moment, it's only English. Sorry, I got it wrong. It's French to English, not English to French. And with this one, we wanted it to be able to run real time on an iPhone. So it still needs to be a recent iPhone. And thanks to the effort we put into these capabilities, it also means that it can actually do more than 300 batch parallel generation in real time on a single H100. Which we think is also exciting in the future for deploying such models on API at limited cost. So let's see a short demo.
Bonjour à tous. Je suis ravi de pouvoir m'adresser à vous aujourd'hui en français.
Hi everyone, I'm delighted to be able to speak to you today. And for instance, my phone will translate what I am telling you into English. As you can see, it is in airplane mode. It doesn't have an internet connection because our...
Okay, and at this point, I'm going to try to give you the real thing, because I have a phone here. Let's see. Bonjour tout le monde. Merci de suivre ma présentation.
Hello everybody. Thank you for following my presentation on the publication of our results in an open manner. These results have been developed within our artificial intelligence laboratory that is located in Paris. We have always emphasized being able to train models of reasonable size that can run on a phone or a computer entirely locally. Thank you very much, and I will resume the presentation.
Okay, so that's it for the project, and now I want to quickly cover a few of the challenges we have. So for most of our models, we actually have at least 3 implementations of them, when not considering 4. The first one is the training implementation. The training code base, we have a lot of legacy code. It's very dangerous to touch anything because you don't want to break like past checkpoints or things like that. Okay, so that's the first one, and that's the reference one. Usually that's the one that works. Then we have a Kendall Rust implementation, because our CTO loves Rust. But there's also some advantage to that, which I'm going to discuss after. But typically, Python in an inference use case tends to be too slow to schedule the kernel. So in training, it's perfectly fine, but at inference, especially in some cases, you're running locally, you have a batch size of 1, the time that it takes for Python to schedule the whole thing versus the time that it takes to run on GPU are of the same order or even larger, which means you're going to get huge lags. So you don't have this disadvantage in Rust. That's why a lot of the demo we run on the web, for instance, they are actually hosted through a Rust backend on a GPU. Okay, then we have the MLX version, which allows us to run on iPhones and Macs. Obviously, we also need a Swift MLX for iPhones. That's another version. We obviously need a decent PyTorch version because that's the one that's going to be the easiest to hack around. And we actually managed, through some trick I'm going to discuss after, to get it pretty close to the Rust version. And finally, for some of our models, we might have some transformers based, like in the library transformers by Hugging Face, which is definitely going to increase our reach. A lot of people don't want to try to understand what is our particular library or to install it and its dependency. It's much easier to install transformers. But at the same time, for us, we cannot just have this implementation because we need an implementation we have control over if we want to like do some early demo or whatever, and also it's easier just to do maintenance on our own implementation. So that's already quite a few implementations, and we have to make sure they all do the same thing and they kind of have the same features. And that's the part that's a bit hard. There's many features like whether we support quantized, whether we support on-device, whether we support batch or streaming, whether it's actually up to date. And usually we are only going to get a few of those for each of the backend. I know on quantization, for instance, I think things are still a huge mess. Like, I know there is a page on Hugging Face that tries to explain which quantization I should use, but there's already maybe like 8 different backends between F8, bits and bytes, there's Torch AO. Most of them have incompatible representation for the checkpoints. For instance, I think on the VLLM page, there is still an open issue for using the latest Gemma quad model, and it's been like that for 2 weeks. So yeah, overall, it's complicated, but we're trying our best to offer like a bit everywhere our models. And then finally, one trick I'm going to tell you about my favorite tool for inference code. Sadly, it's a bit hard to use at train time, but for inference, it's Kyutai graph. As I said, if you're doing Python, scheduling kernels is way too slow. So you could use Torch Compile or some of the other tools that were presented before. The main disadvantage I see to that is that Torch Compile doesn't necessarily support all the kernels. I know at some point I was a pretty big user of Xformers, and the Xformers kernels couldn't be put into Torch Compile. It's going to be slow at start, especially if you compile your whole model. The behavior might change over versions, which is a bit scary. And if you do get an error, the tracebacks are often cryptic and not that informative. So in contrast, Kyutai graph is like the simplest thing to reason about, super fast to run, and it basically removes all scheduling overhead. What it doesn't do is kernel fusing, and one thing is you do need to be a little bit careful. Basically, any tensor that is allocated, so let's say you have your model, you have your forward, you're going to Kyutai graph it. Anything that's allocated within the forward and is going to disappear at the end of the forward, you don't need to worry about. But if you have any external state, which could be a KP cache or even the input to the model of the input to the model and even the output, those tensors need to stay the same. So yes, once you respect that, basically what's very easy is you're going to Kyutai graph. So it's going to run your code, remember all the kernels you called in a row. It's going to keep your input kernel, your input tensor allocated, and then the next time you want to run your model, all you have to do is copy your input into the input tensor that you had allocated previously, and schedule the Kyutai graph. And then in the previous output tensor where you used to have like the previous results, now you're going to get the new results. And I can show an example. So here I have a fairly complex transformer on top of that with a second depth transformer, which is theoretically a small transformer, but because it's small in terms of weight, but it's pretty big in terms of number of operations. So this is a CPU trace of Python trying to schedule all individual kernels. We have a GPU trace where we see that the the GPU is mostly idle because the CPU is not going fast enough. And then if we just add those few lines, which is taken from one of our inference code base, because it's not that easy to use out of PyTorch, so I just made a small wrapper where you can just grab your forward function, and assuming that you don't have any other external state that you're not going to pass to the graph function, then you will have something that is correct and also look much nicer. So now you can see all the previous kernels, which were all that. They're replaced by a single Kyutai graph launch. And basically that means your GPU is getting work as fast as possible, and now we have a much nicer GPU trace. So yeah, I recommend it. It always works and gives huge speedups. So yeah, as a conclusion, so it's been 1.5 years that we exist. We released so far like 5 models across a wide range of tasks and also inference setups. We're gonna keep more coming pretty soon. And also maybe one regret that I have that I mentioned is at the moment we have released fine-tuning code bases but not full training code bases. So I hope over the next year I'm gonna have more time to do that, because I think it's really helpful to the community, especially like the research community, also other startups. So yeah, and that is it for me. If you want more information, you can check our GitHub, you can check our Hugging Face and our blog.